So differentiating under the integral sign is not really part of complex analysis, not part of it at all, but it's such a useful technique that I thought it's worth mentioning here, since we're talking about integrals in general. And really, you're welcome to use it instead of complex variables if you wish. And if we're talking about exams, then normally, yeah, I just if it's an exam question, I just give you the integral and you can do it any way you like. And I know if I'm suggesting that you do it by a complex technique, I might give you hints, but I'd probably always say do it this way or otherwise. And if you can think of some neat other way of doing it, then that's fine. This technique is worth bearing in mind, in particular with complex variables. I mean, just because if you realize that evaluating residues at a multiple pole is a bit of a pain. So if you see that you have an integral where you've got a pole of order which is higher than 1, quite often, I've given you one technique of finding residues of poles of order more than 1, and that was actually effectively differentiating under the integral. But if you don't think of doing that technique, another way of doing it is actually to evaluate a different integral, and then use this differentiation under the integral sign to get the integral you want. So that's sort of really why I've mentioned it here as well. Okay, so on with the technique. So it relies on Leibniz's rule, which is basically saying that if you've got some function of x, you're integrating with respect to x, but that function contains a parameter mu, then if you differentiate outside the integral, or in other words, it's differentiating under the integral, it's called, then this is really what it's saying is that if you differentiate the answer you get, so obviously if you integrate this f with respect to x, you'll get some function of mu as the answer. Now if you differentiate the answer with respect to mu, that's the same as if you differentiate the function with respect to mu before you integrate it. That's assuming a and b are both independent of mu. If they're not independent of mu, then you need these extra terms, but normally speaking, a and b, well, especially in complex stuff, a and b are going to be 0 and infinity, or minus infinity and infinity, so you can forget these two bits. But that's basically all differentiating on the integral means. You can interchange the integral sign and the differential is basically it. So let's look at a very simple example to see how it works. So we've got this famous simple results we mentioned before. But if we differentiate, so we've got a parameter, our parameter in this case is a. If we differentiate with respect to a, then what are we doing? We're going to differentiate this thing with respect to a and get minus pi over a squared, and then we're going to differentiate with respect to a, but we're going to swap the order of differentiation and integration. So we're actually going to differentiate this before we integrate. And so in other words, we're differentiating 1 over a squared plus x squared, which gives us this, and this is valid. This is a true statement. So you see, with very little effort, we've actually then of course we can rearrange this, we've ended up getting the answer to this integral. Now, if you're given this integral to start with, getting the answer is not particularly easy. I mean, you can do it. I mean, with complex variables, you can do it. You've got double pole, obviously it's z equals ia, you need to evaluate the residue of, or you can use elementary techniques and change variables. Quite a lot of effort. If you know this trick, then all you have to do is know what this is, which is easy, inverse tan and all that, and then all you have to do is differentiate this with respect to a, and you get the answer. So it's a useful trick. The thing is really being able to spot that the integral you want is the differential of, with respect to some parameter, of an easier integral. Now, what happens if the integrand you wanted, if the integral you want to do, the integrand of the integral you want to do doesn't have a parameter in the right place? Well, you can actually just introduce a parameter and then set it to 1 later. So we'll see how this works. Suppose you want to find this integral now. So how are we going to get an x squared upstairs is the question. Well, if we had a b here, a b or a b squared here, we could differentiate with respect to b and get an x squared upstairs. So from this integral here, we can make a substitution. We can replace x by bx. Okay, this doesn't change the limit. So we're replacing x by bx. Then we've got bx x squared, b squared x squared on here, and we replace the x by bx. So the b we just move over there. So we end up with this result here very quickly. Then we can differentiate both sides with respect to b, differentiating inside the integral with respect to b. We end up with 2bx squared upstairs, and we'll have this lot squared downstairs with a minus sign, and differentiating with this respect to b, we get a minus, and then all we do is then set b equal to 1, and the minus signs cancel, and we get this answer here. Okay, another example. So if we're given this result here, and differentiate with respect to a, then we can get this result here. We can also get this result fairly easily. Where did this shine x come from? Well, if we can introduce a b in here, inside the cosh, change the cosh x to cosh bx, then if you differentiate cosh bx, what you get? Well, you get an x times shine bx, and then you can set the b. So that's what we got upstairs, and we can set the b equal to 1 later. So okay, so we introduce another parameter b, using the same sort of change variables, and then differentiate with respect to b and set b equal to 1. So the last thing you might want to do is evaluate this integral. You've got cosh x upstairs. So how do we get the cosh x upstairs? Well, if we were to introduce a parameter here instead of here, if we put some parameter c, say a plus c cosh x, and then differentiate with respect to c, that would bring the cosh x upstairs. So I've written down this sort of general format. Not sure it's particularly useful, but okay, just for fun. So you've got IABC equals, so you've got an integral which is a function of three parameters, A, B, and C. So you can differentiate with respect to A and or B and or C as many times as you like, and you can get this expression here. So you just pick basically what you want. Okay, so you can have a go at doing question 26 and 27.